Hi everybody and welcome to another video of the Optimization Masterclass. So this class is going to be based on the course that I do at Imperial College, which is based on this book, Convex Optimization, of Stephen Boyd and Lieven Vandenberger. If you haven't followed the previous lectures in this series, please check the link over here. Remember that you can download the material that I use to teach the class, so the so-called smart handouts, from the link in the description down below. If you have suggestions on future topics that you would like that I cover in this masterclass, please leave it in the comments below. Thank you very much and enjoy the course. In this chapter, we're going to cover the topic of convex functions. In particular, we will first study basic definitions and some example of elementary convex functions, and then we will develop a calculus of convex functions, which will allow us to essentially establish if complex functions are convex or not, basically decomposing those convex functions in basic functions. We will also look at generalization of convex functions, in particular quasi-convex functions and log-concave functions, because even though those functions do not satisfy convexity, we can still solve problems, optimization problems that have those type of generalizations in an efficient and reliable way using a convex optimization. So let's start with the basic definition of a convex function. So a function f is convex if two conditions are satisfied. The first is that the domain of the function has to be a convex set. Okay, and now we know what a convex set is because it's what we covered in the previous chapter. And the second condition is that for all x and y that belongs to the domain of the function, and for all thetas between 0 and 1 included, then we want that this condition is satisfied. Okay, so essentially that if the function evaluated at over the line segment between x and y has to be less or equal than let's say that the line segment computed with respect to f of x and f of y. Okay, so this can be represented in the plane very easily. If we have this function and we compute the value of the function at the point x and at a point y, so you can imagine that here we have the axis and here you have the point x and here you have the point y, then we evaluate f of x and we evaluate f of y. Then essentially convexity is telling us that the function has to lie below the line segment or chord between f of x and f of y. From an intuitive point of view, this essentially means that the function has to curve up. Okay. This inequality actually has a name. It's called Jensen inequality. And actually, Jensen inequality, this is a very special case of Jensen inequality. Okay, this is the simplest possible case of Jensen's inequality. Jensen inequality can be generalized. For instance, instead of considering just 2 points, you can consider an arbitrary number of points, and it can be extended to infinite sums. It can be extended to integrals, to expected values. In fact, probably the most general form, one of the most general forms of the Jensen's inequality is the one involving expectations. And in fact, a function f is convex. A function f on some probability space is convex if the function evaluated at the expectation of x is less or equal than the expectation of the function evaluated at x. We can also define strict convexity if the equation in1 holds strictly with the less. And of course, if x and y are not 0 and if theta is not 0 and is not 1. Okay, so also this has to be strict because, of course, if, for instance, theta is 0, then we will have that we will have f of y less equal than f of y. And of course, if we have the strict inequality, that's not true. It's not true that f of y is less than f of y. So yeah, I mean, for strict inequality, x and y have to be different. I said that theta has to be non-zero and not 1, okay? I said that x and y do not have to be 0, but actually what I meant is that x and y, I mean, the condition has to hold strictly when x and y are different. We can define concavity, and concavity is essentially the opposite of convexity. So a concave function is this one. It's one that curves downward. And in fact, a function f is concave if minus f is convex. And the same holds for strictly concavity and strictly concavity. We can now let's look at some more property of convexity. So first of all, we notice that affine functions verify the inequality with the equality sign, okay? This can be verified. I mean, you can do it as an exercise. You can check that this inequality here, holds for f of x equal to ax plus b with a equal, okay? This implies that affine functions are convex, but it also implies that affine functions are concave, because, of course, if it holds with the inequality, if you change the sign, it's still going to hold. And the converse is also true, and the converse is that any function that is both convex and concave at the same time, it has to be affine. I mean, this is intuitive, okay? I mean, convexity is a function that curves upward, and concave is a function. I mean, a function that is concave is a function that curves downward. So the only function that can satisfy both conditions is a straight line or an hyperplane, okay? And so an hyperplane is defined by, an hyperplane is an affine function, essentially. Or better, an affine function defines an hyperplane. That's the proper way of expressing this idea. A very useful property of convexity is the fact that let's consider now that you are at high dimension, okay, and you want to try to understand if a function is convex or not. You cannot really look at the, at the shape. I mean, if you are like in five dimensions, you cannot represent it. But actually, there is a nice result which says essentially that a function is convex if and only if, once we restrict it to any line that intersects its domain, is convex, okay? What does that mean? It means that essentially a function is convex if and only if for all x in the domain and for all v, the function g of t, which is defined as f of x plus tv, is convex on its domain. So what is this? This is g of t is nothing else than the restriction of f of x along the line starting from x and going in the direction of v. As we change t, we go along the direction. For instance, for t equal to 0, we just have f of x. And for t positive, we are going along the direction v. For t negative, we're going to the opposite direction v. And this has to be true for all points. This is useful, we will see later on once we develop better the theory and algorithms for convex optimization. Another important definition that we need to give is that of extended value function. This is just, this is useful to simplify notation. We saw that, for instance, the Jensen inequality has to hold for all x and y in the domain. And so we always have, if we use standard notation, we always need to, state every time that certain conditions has to hold for x and y in the domain, and maybe the domain is complex and so on. It's a complex set. Not complex numbers, but complex in the sense that it's complicated. A way to avoid that is by using extended value functions, which essentially says that f tilde is the standard value extension of f if it's equal to f of x on the domain, and if it's infinity outside the domain. Maybe I didn't point out that this definition is for convex functions, okay? This definition makes sense only for convex functions. Well, I can say immediately that if you have a concave function, that the definition has to be replaced. You have to replace infinity with minus infinity. Okay, so it's written over here. Keep it in mind, because if you do some exercise, you may, replace infinity and then things do not work. The reason is that for concavity, you need to replace minus infinity, okay? Because, of course, a concave function is defined as a function a function is concave if minus f is convex, okay? and that's why you need the minus here, so that when you do minus f, you get the plus, and everything works. Okay, so why did we introduce extended value functions? To simplify notation, because now if you use f tilde and you apply the Jensen inequality, actually you don't have to specify that this has to hold for all x and y in the domain, okay? And if the domain is complicated, well, at that point we don't care anymore, okay? It just has to hold for all x and y, and if the function is is not defined, that you're going to get infinity, and the solution and the inequality is going to be satisfied, because for instance, if we go back to this inequality and now we apply to the standard value function, we see that if x or y do not belong to the domain, then we're going to get infinity on the right hand side, and so for sure the condition is satisfied either with a greater or with a equal. Well, as long as we are happy to actually think in terms of, comparing infinities, okay? But we just define an extended algebra in which this makes sense. Extended value functions are used commonly in books and literature about convex optimization, and often, we just abuse the notation with f. We may actually be indicated f tilde, and from now on, we just, when we say f, we actually mean the extended value function, unless we want to make a distinction. In that case, we're going to use f tilde. So in the following, when you see f, you can assume that is the standard value function, or otherwise that whatever definition we give has to, of course, be, has to hold for points in the domain. As I say, there are some exemptions in which we want to distinguish between f and f tilde, and that is when we will look at the composition theorem. For the composition theorems, some of the conditions need to hold on the extended function, the standard value function, and in that case we will make a distinction. Let's look at an example of extended value function, and we look at the function which is defined as x squared in R++, okay? So it's essentially this branch of a parabola in which the point at 0 is missing. So this is f of x. If we want to define the extended value function, that means that the function is going to be infinity over here, including the point at 0. Okay. Now what we're going to look at is essentially the fact that convexity, in case the function f is differentiable, can be characterized in terms of derivative, first derivative, and if the function is double differentiable, it can be characterized in terms of second derivative. But I want to stress that the theory that we are developing, convex optimization, does not require differentiability of the functions, because convexity is a property that doesn't require differentiability. Okay. For instance, a square, it's a convex set, but of course it's not smooth. Okay. Okay. So let's look at the first, the first order characterization of convexity. So if f is differentiable, then f is convex if and only if, again, the domain is convex. So it's important that we always remember that it's two conditions that we need to check. One is the domain has to be convex, and then we have an additional condition. And for differentiable function, this is the condition that we have. Okay, so this condition is essentially telling us that f of y has to be greater than or equal than the first order approximation, the first order Taylor approximation of the function itself. And this has to hold for all x and y on the domain, or if we use the extended value function, then we don't have to specify that. Okay, so what is the meaning of 2? So 2 actually replaces the Jensen's inequality. Of course, it makes sense only if f is differentiable, while the Jensen's inequality can always be applied. But it's telling us actually something interesting. It's the fact that the first order Taylor approximation of the function is what is called a global underestimator of the function. It means essentially that if we look at a point x and we compute f of x, the Taylor approximation, So we end up with this that is going to be always below our function, okay? And this is actually a very, very, I mean, this property is very important, okay? It's the reason why, convex optimization is so powerful. It's the fact that essentially from local information, so what's happening here, we actually get something that is global. So we are checking just convexity at a point, but actually we got a global estimator, something that we know for sure it's always below our function. And there is actually another implication of this fact that is very important, and the fact that, you see, if we take this inequality and we find a point x such that nabla of f of x is 0, so essentially it's it's a turning point, or I mean it's it's a turning point. We see that what we're going to end up with is that f of y is greater or equal than f of x, and this is true for all y in the domain, okay, because the function is convex. So knowing this, because again it's an if and only if, so this means that if the function is convex, this is going to hold, and so if we find a point for which the gradient is 0, then what we end up is with this condition that tells us that this is true for all x and for all x, for all y's in the domain, okay. So this is telling us essentially that x is a global minimum, okay? It's a minimizer, it's a global minimizer. And this is a very fundamental property of convex functions that, I would like to make in red, but I couldn't find a nice way to make it red in the handouts. But essentially it's telling us that for convex function, a minimizer is always global, okay? And this is very important because it allows us to find, to find the best solution. I mean, when we look, we find the minimizer of the solution of a convex optimization problem, we're actually finding the absolute best solution. Similarly, we just characterize convexity for using a first order condition. We can characterize strict convexity in the same way by requiring that the inequality that we just defined using the Taylor expansion, the first order Taylor expansion, hold strictly, so with a strict less, of course, whenever x is different from y, and concavity and strict concavity can be defined in the same way by replacing the sign of the inequality. Okay. We now look at a second order condition. If f is twice differentiable, then f is convex. If and only if, again, we require two conditions, which is the domain is convex, and the second condition is that the Hessian is positive semi-definite, okay, which is essentially given by this. Okay, this has to be positive. I mean, that's to be positive semi-definite for all x in the domain of f. Okay, so this expresses exactly the idea that we had before, the fact that a function is convex if and only if the graph has a positive curvature, okay? Essentially is going upward. Similarly, we can define concavity using a second order condition, and a function f is concave if and only if the domain of f is convex. So I want to point out that it doesn't matter if we're defining convexity or concavity, the domain has to be convex, okay? The only thing that changes is the inequality condition, the Jensen inequality, the Taylor approximation, or the Hessian inequality, okay? And so in this case, essentially the inequality swaps sign and it becomes that it has to be negative semi-definite for all x in the domain. Now, what we need to be careful about, and this is a warning, is that strict convexity and strict concavity cannot be easily characterized using a second order condition. Okay, in particular, the point is that a function f is strictly convex if the domain is convex and the Hessian is positive definite. But the importance here to notice is that this is just a sufficient condition. Okay, so that means that there may be functions which are strictly convex, even though the condition on the Hessian is not satisfied. I mean, of course, you still will have that the Hessian is positive semi-definite, but we will not have it. It's not going to be positive definite. For instance, we can look at the famous example f of x equal to x power 4. This function is strictly convex. We could check it with the Jensen inequality, or we could check it with the first order Taylor approximation. But if we compute the second derivative at 0, then we're going to get 0, and so that shows that the Hessian is not actually positive, but it's just positive semi-definite. Okay. Let's look at a couple of examples. Simple examples. The first example is a quadratic function f of x, in which we have, alpha x transpose px plus q transpose x plus r, where p is a symmetric matrix and q is a vector and r is a scalar. If we compute the Hessian here, the Hessian is going to be just the matrix p. And so then we know that essentially the function f is convex if and only if p is positive semi-definite, and is concave if and only if the function is negative semi-definite. Let's look now at another example that sort of crystallize the warning that I gave before, which is the function f of x equal to 1 over x squared, which is defined on the domain all x apart for x equal to 0, okay? Because at x equal to 0 the function is not defined. Well, if we compute the Hessian here, we will end up with the second derivative being always positive. However, for all x in the domain, however, this function is not convex. And the reason why is actually that it violates the condition on the domain. You remember that we always need to have two conditions. One is the inequality condition, and the other one is that the domain has to be convex. Of course, the domain of this function is not convex. There is a hole. We are on the line, and there is a hole. And we know that a set that has a hole cannot be convex, because if we take a point on a negative point and a positive point, and we trace the line segment between these 2 points, it's going to go outside the set because it's going to pass through 0. We now look at some examples of convex functions. We already seen that affine functions are convex and concave, and so in particular linear functions, which are just a special case of affine, are convex and concave. We've seen that the quadratic functions are convex if the matrix P, for instance, is positive semi-definite. We can actually define affine functions on Rm times n, so for matrices, and in that case we need to replace the inner product with the inner product on Rm times n, which is the trace of the matrix A transpose times x, which is defined in the following way. Okay, so again, this is an affine function, and so it's convex and concave. Exponentials are convex for any A, because the graph is like this. It curves upward, for a positive and for a negative. Okay, so it's fine. Powers x power a are convex on R++ for a greater or equal than 1 and for a less equal than 0. So essentially, if we have something like this, well, it's convex. So like, for instance, that square, it's convex. Or if we have something like this, also 1 over x, it's convex again. Instead, the powers for a between 0 and 1 are concave, and maybe an example I can do it over here, and it's going to be something like this. So it curves downward. The powers of absolute value are convex for powers that are greater or equal than 1. Like, for instance, if you think about the absolute value. Okay, so the absolute value is concave, even if it's not, you know, differentiable in 0. Actually, going back one moment to this case, I mean, of course, also x squared for all r is convex. Okay, so I mean, this is not telling us that a power of x, you know, a power of x power a is not convex on something that is not r plus plus. Okay, I mean, of course it is. It's just that if we consider x cube, okay, then x cube that behaves in this way is not convex in all r, but it's still convex in r plus plus. That's why we have this condition here. So I just wanted to clarify that. The logarithm, log of x, it's a concave function on its domain. And this is a standard example of concave function. I mean, we will see the log a lot. And so it's, I mean, it's like the classical example of concave function for us. And actually, I already mentioned this in previous lectures about the fact that I think in the statistical applications, when we introduce the logarithm, we say, okay, this is going to be a concave function. The negative entropy is a function defined as x log x, and this is going to be convex on r plus plus. We can also define it in r plus as long as we decide that it's 0 at 0. Okay, so otherwise it's an undefined form. And is, as I say, the negative entropy is convex. Okay, I mean, if we do the plot, it's going to be something like this. So sort of quadratish for small x, and then linear for big x, and it has this shape and is convex. Every norm on Rn is convex, and we can prove it essentially. The proof is the following. So if f is a norm, we are going to consider a theta between 0 and 1, and we're going to check if Jensen's inequality applies or not. So what we're going to do is that we consider the norm of theta x plus 1 minus theta y, and then we apply the triangular inequality that holds for norms, and that's going to give us this result over here. And then we apply the result that if you have the norm of alpha x, that's equal to alpha the norm of x, as long as alpha it's a positive number. And so we can bring outside theta, and we can bring outside 1 minus theta, and then we have our Jensen inequality. Okay, and so norms, so every norm, no matter how what norm is, as long as, you know, it has triangular inequality and the property that the scalar multiplication can be brought outside, which is in the definition of norms, is going to be convex. The maximum singular value of matrix is convex. This is a complex function if you think about it, because I mean, if you want to compute it, you will have to, you know, solve the characteristic polynomial and then find the maximum. But actually, this can be shown very easily based on the fact that the maximum singular value is equal than the two norm for matrices. And since any norm is convex, then the maximum singular value is convex. The max function is convex. Okay, so let's prove this. So if f is giving you the max between a finite number of elements xi, then we compute f of theta x plus 1 minus theta times y. So this is essentially the max of this for all the xi and yi. And then what we use is the fact that the max of the sum of two terms is always less equal than the sum of the max of the two terms. Okay, and then after we also use the fact that theta can be brought outside. Okay, I mean, this is obvious if you know, we have for instance two functions like this. We see that the sum of the individual max, so if I sum this plus this, is definitely going to be bigger than if I first sum the two functions, which is going to be something like this, okay? And you see that the maximum here is going to be just either the previous peak or another peak that may be a bit bigger, a bit smaller than the other peaks, okay? So we see that in general the max of the sum of two elements is always less or equal than the sum of the max. And then the theta can be brought outside because it doesn't change the max, okay? And then at the point we recognize, even if this is cut, you can complete it, f of y, we recognize the Jensen inequality. Let's look at another example, which is a quadratic-over-linear function. So a function of the type x squared divided by y. So x squared is quadratic, y is linear, and this is convex. And this can be shown using the second order test, so the Hessian test. We compute the Hessian of f of x and y. You can do the computation as an exercise, and you are going to end up with this expression. And now the trick is to recognize that this matrix can be written as the product of these two vectors, and this proves that these are going to be positive semi-definite, okay? Because this is essentially a form of the type 2 over y cube z times z transpose, okay? And this is always a positive semi-definite matrix. Of course, I skipped something, and the fact that this is true as long as y is positive, okay? Because this is positive semi-definite, we need that this y cube is still positive. So, of course, if y is negative, that's not true, it's concave, and if y is 0, then it's not defined, the function is not defined, okay? Another very important function is the Log-Sum-Exp, so is the logarithm of a sum of exponentials. So it's not trivial to show that the Log-Sum-Exp is convex, because actually we know that, we know that the log of x is concave. So it's actually a bit weird that the Log-Sum-Exp is going to be, it's unexpected that it is actually convex. We may think about it that it may be because, the logarithm of the exponential of x is actually x, but here we don't have just an exponential, we have a sum of exponentials. So how do we show that? So we have this proof mechanism that actually, I'm showing here as an example because it can be applied to other functions as well, so it's good to know the idea. The way to do it is that we compute the Hessian of f. So if we compute the Hessian, we can find this expression in which we are using the notation that z in this expression is a vector of all the exponentials. And now we want to check that the Hessian is positive semi-definite, or not sure if here there is an error or not. I say positive definite, but maybe we just need to check that it's positive semi-definite. And this is something that I will correct in the handouts if this should be semi-definite. But the idea is the same. We want to check if the Hessian is positive semi-definite, and to do so we pre-multiply and multiply the Hessian by v transpose and v. So for a general vector v, if we do this multiplication, we end up with this expression. So you can check, that this is correct. And now the trick to show that this is going to be non-negative, so here it should be actually semi-definite, it's missing, okay, is to use the Cauchy-Schwarz inequality that is given over here. And you can apply it with this value and this value and check that actually is going to give us that the Hessian is non-negative, okay? And so the Hessian is is positive semi-definite, and so the Log-Sum-Exp is convex. Another example is the geometric mean, and the geometric mean is defined in the following way. So is the n root of the product from I to n of xi, and it's a concave function on the domain, which is R++. And the proof follows the same steps of the proof of the Log-Sum-Exp, and so I skip it, and you can do it as an exercise. So you compute the Hessian, and you want to show that you know, that the concavity condition is satisfied. Another, I mean, maybe the last easy example is the log-determinant. So the log-determinant f of x is log-determinant of x, and this is a concave function on the domain, which is s++. Okay, we will, I mean, we will see this type of functions quite often, and the idea is the following. Okay, so when we are dealing with positive semi-definite matrices, we will often see the determinant of the matrix S as a replacement of the vector x, okay, for vectors instead of matrices. So essentially, that x really plays the role of our standard x, and now we understand that the log of that x is actually concave because the log of x is concave. Okay, so again, you have to think a bit about this analogy between you know, positive semi-definite algebra and standard algebra, because it's helpful to know already what the result is going to be. Actually, we're going to prove it. Okay, no, I didn't notice that I actually wrote down the proof. So let's prove this this condition. I mean, the fact that the log determinant is concave. The way in which we do it is that we're going to exploit the property that I mentioned before about the fact that to check if a function is convex, we can check if it's convex on any line starting from a point in the domain. Okay, so we define g of t as the function f of z plus tv, where you know, f is defined as the log det, and z is you know, it's a point in the domain of f of x. Okay, so that means that z is going to be yeah, in s++, and without loss of generality, we can assume that actually z plus tv is in x++, is s++. Okay, and so let's try to do the proof. Okay, so we compute g of t, which is given by here, and then we use the following trick. We factorize on the left hand side and the right hand side z power 1/2 and z power 1/2. We can do this, I mean, z power 1/2 is defined for the matrix z because z is in s++. Okay, so you can compute the square root essentially. So this is the resulting expression that we get. And then what we're going to apply is essentially the fact that we are going to compute the determinant of this expression. And you know that when you compute the determinant, you can change the order of the matrices multiplying inside, because, I mean, the determinant behaves very well with respect to multiplication of matrices. So the determinant here is essentially equal to the determinant of z1/2 times z1/2, which gives you back z, and is actually going to be here. It's not visible. Again, sorry for the fact that this handout here is cut. In the normal handout, this is not cut, but essentially that's what you're going to get there. Okay, so essentially is the log determinant of z. Again, write it here. Maybe there is some mistake, but I'm pretty sure it's something like that, and you can check it. Because we're just you know, putting together these two matrices and put it aside, and then I mean, again, the determinant behaves well with respect to multiplication. It becomes a sum, and so we have the log det of this term, and the log det of this term, the det of this term, can be written in the following way, in which the lambda i's are the eigenvalues of this matrix over here. So now at this point, what we can do is to just compute the second derivative of g of t. And of course, this is the derivative with respect to t, so this term doesn't matter actually, because it's not, I mean, does not depend on t. We compute then the second derivative of this term, we end up with this term, and we see that everything is quadratic, but there is a minus outside, and so we have that the g double prime is less equal than 0, and this shows that f is concave. We now look at two important examples, which are not functions actually, but they are sets which are related to functions. And these are important because there are some convex optimization problems that can be solved thanks to being able to actually rewrite the problem using these two properties of convex functions. So the first set that we see is the alpha-sublevel sets. And the alpha-sublevel sets are essentially defined as all the points x that belongs to the domain of f that are such that f of x is less or equal than alpha. Okay, so you already seen this in the first course of optimization in autumn. So if you have a convex function like this, and you want to find the sublevel set associated to this level of alpha, then essentially this means that what you want to find, what you are going to find, is this set of x over here that are related to the f of x which are below or equal to alpha. So this is essentially, in this case, is c of alpha. Okay. Now the property is that the alpha sublevel sets of a convex function are convex for any value of alpha. Okay, and this is easy to show. So let's consider any 2 points x and y which belongs to this set, and since they belong to this set, then f of x is less equal than alpha and f of y is less equal than alpha. Then we want to compute f of theta x plus 1 minus theta y, with theta between 0 and 1, any theta. And then, I mean, since f is convex, then it means that this function is less equal than theta f of x plus 1 minus theta f of y. And now we know that this has to be less than equal. Then, we exploit this relation and this relation of alpha theta plus 1 minus theta times alpha. We do the sum and we end up with alpha. Okay, and this shows that the point theta x plus 1 minus theta y belongs to the alpha sublevel set, and so this set is convex. Okay, the converse is not true. Okay, so there are functions which, for instance, let's consider e power minus e power x. This function is strictly concave because, it's the negative of a strictly convex function. But if you consider the sublevel sets, they are convex. Okay, so a function that is convex as all the sublevel sets are convex. The opposite is the converse is not true. A similar result holds for concave functions. Okay, so if f is concave, then its alpha super level sets are convex. Okay, this is not a typo. Okay, because essentially what we switched here is we went from sub to super, and that's why we still ask for convexity. And how are defined the super level set? Well, it's exactly the same definition, but we have the greater equal instead of the less equal. Again, the converse doesn't hold true. If we have a function with alpha super level sets which are convex, it doesn't necessarily mean that this function is concave. As I say, this example that may seem quite technical is actually quite useful in practice because it allows us to establish the convexity of a set, which in general may be difficult if the set is complex. If we can write, if we rewrite the set as the sublevel or superlevel set of a convex or concave function. Okay, so it's essentially a good trick. The last important example, and this is very important, it actually justify why we, justify the relation between convexity of set and convexity of functions, is that of epigraph. Okay, so this is the last important example, epigraph. And is actually very important also in practice. We will see various problems that will be various convex optimization problems that are solvable once we rewrite it in the so-called epigraph form. So what is the epigraph? So before defining the epigraph, let's define the graph of a function f. So the graph of a function is given by the pair x f of x, so the coordinates, for each x belongs to the domain of f. So it's just the graph. I mean, as you can imagine it, I mean, the graph, when we do something, you know, a graph like this, I mean, the graph is nothing else than the collection of all the pairs x and f of x. Okay? The epigraph is what lies above the graph. Okay? Epi means above. And so the epi of f is defined by all the x and t, with x belongs to the domain of f, such that f of x is less or equal than t. Okay? And this identifies all the points which are above f of x. So for instance, an example of epigraph is represented here. And we see then that, for instance, if we take 2 points of the function and we trace the chord, we see that locally here, this part obeys the convexity rule of a function, because the function is below the chord associated to these 2 points, and it also respects the definition of convexity of a set, because the chord lies inside a set. If we look, for instance, at these 2 points here, and we trace the chord, then we see that the chord here lies below the function, so this function is not convex, it's concave. And at the same time, if we look at the set, the chord is outside the set, the epigraph, and so it gives the same result, that the set there is not convex but is concave. In fact, the point is that the epigraph provides a link between the notion of convexity of set and convexity of functions. Because, I mean, maybe I didn't say that, but essentially a function that is convex, a function is convex if and only if its epigraph is a convex set. Okay, and this is what provides the relation between the notion of convexity for sets and the notion of convexity for functions. Just for completeness, even if we are not going to actually use it, a function is concave if and only if the hypograph is a convex set. Again, this is not a typo. The fact that we say a convex set is because we already made a switch. We made a switch in here, because the hypograph is nothing else than the graph that lies, I mean, the points that lie, the set, sorry, that lies below the curve of the function.